All right, so this is Chapter 7 from TAP's Matrix Groups for Undergraduates. And so here he discusses all the basic manifold constructions, and I think I've been partly assuming that some of these things were known in some of the previous talks, which is unfortunate, but anyway, the things are relatively carefully done in here. I'm not going to do everything. Really, I've assumed that you have had some previous experience with tangent spaces, differentials, and just elementary manifold theory. So I'm just going to collect some big central points here, and actually give you a definition of a matrix group, which we hadn't actually done yet. Oops. But rest assured, the things I've been calling matrix groups were actually matrix groups. So don't worry, it wasn't too much of an oversight. So let G, a subset of this, be a matrix group with Lie algebra. Oh no, here I did it again. With Lie algebra G. Subset of G, L, and K, then for all x, e to the x is in G. All right. So the exponential, it may not be onto G, but it's certainly into G. All right. And so for sufficiently small r greater than 0, v is equal to the image of the exponential with this small ball intersect with G. It's going to give you a neighborhood of the identity in G. And so the restriction of the exponential to this, close to the identity open ball in the Lie algebra gives you a homomorphism onto that subset of the Lie group. So in other words, if you suitably restrict the exponential, it gives you a patch from the Lie algebra to the Lie group. Now, topologically, it's pretty simple what's going on here. We have this GL and K, the general linear group of order K. It's a subset of this space, n by n matrices over K, which is like isomorphic to, of course, Kn squared, and then that is either directly Rn squared, or it's through just stringing out real and imaginary components R to the 2n squared, or through stringing out the real and the 3 versor components, like the quaternionic case, it's R 4n squared. Anyway, the point is, there's a natural way of viewing G as a subset of Euclidean space. So really, you can look at these matrix groups as embedded submanifolds of Euclidean space, which means that they're particularly easy to analyze. Now, we also, in Chapter 7, have some discussion of open, closed, compact, boundary point, sequential convergence, limit point, Cauchy sequence, relative topology, continuity topology, continuity, homomorphism, path-connected, Clopin set, the Heine-Borel theorem, open cover compactness, sequentially compact, continuous image of compact is compact, and the image of a compact set attains its min and max. Oh, always a good one to know about. So, basically all your favorite analysis is discussed in the current context, and so anyway, I'll let you read that. But here's our definition. A matrix group is a subgroup of G, all right, which is closed in BLNK. That's GLNK, I think. I think that's supposed to be a G. I haven't defined any BLNK, so pretty sure that's a G. So a matrix group is a subgroup which is also closed. All right. So proposition 4.28 holds that the orthogonal group, the special linear group, the special orthogonal group, the special unitary group, these are all matrix groups. And each of the groups, ON, SON, UN, SUN, SPN, are also compact. All right. So they're compact. Now, notice SLN's not on this list. All right. Okay, so that brings us to discuss the so-called Leigh bracket. So let G be a matrix group with Lie algebra G. For all G and G, we define the conjugation map. So you multiply by G and G inverse on one side or the other, right? If G is an abelian group, this is kind of, well, like nothing happened, right? But in general, that's interesting. And so proposition is that this conjugation is a smooth isomorphism for each g, all right? And the derivative, all right, the differential, if you like, at the identity is going to be a mapping from Lie algebra to Lie algebra. And more than that, it's a vector space isomorphism. And we have a definition for it. The big add, so add sub g, the adjoint, is the differential of the conjugation at the identity. Now there's a couple different adjoints that get floating around here, so I'm going to call this big adjoint, if you don't mind. Big add. So, in fact, the adjoint, proposition 2, the adjoint sub g acting on b is g, b, g inverse for each g and g and b in the Lie algebra. So the adjoint actually acts by conjugation of the Lie algebra. So that's kind of neat. Here's the proof. So the adjoint of b is the differential at the identity of the conjugation map of b. So we can look at a curve that takes as its velocity vector big B. So little b is the curve whose initial velocity is big B. All right. So with respect to the curve definition of the differential, this is the derivative of CG composed with little b at time 0. But that's this, right? On the flip side, g and g inverse have no time dependence, so you can just pull the derivative inside, and of course that works out to b, and there you go, g, b, g inverse. And there's the proof of proposition 2. Okay, so the Leigh Brackett is important. I think that's not an overstatement. The Leigh Brackett of vectors in the Lie algebra a and b is the commutator bracket. So this is notation. It's defined to be the derivative at time 0 of the adjoint of, now here a of t is going to be the curve, which gives you back a as its initial velocity. So we take the differential at the point a of t of b. Excuse me, not the differential. That's this. I'm misreading it. This is the adjoint map. All right. So that's the definition of Leigh Brackett, but it will work out to be the commutator when we actually look at the details of it. Okay. So if all elements of the group commute with G, then of course add G of B is G inverse BG. But if all elements of G commute with B, then well, I think I might. I kind of think I might go back to frac G here. Anyway, certainly if this is equal to B again, it is true that the adjoint is identity. So the map add the adjoint G measures the failure of G to commute with elements of G near the identity. I will agree with that. So the adjoint G of B measures the failure of G to commute with G elements in the B direction near I. It's a kind of funny statement, right? Because, well, I mean, this is a really curious relation that certainly wouldn't make sense in the more abstract context, right? Here, B is in the Lie algebra, and G is in the Lie group, right? What right do we have to interface the algebra and the group? Well, the reason we can do it here is they're matrices, right? So this is matrix multiplication, and that's allowed, but the more abstract version of this needs further constructions. Okay, anyway, I'm gonna move along here. Anyway, just sufficient to say that's based on an abuse of our current context. So here's actually how to calculate the Leigh bracket. If you don't want to differentiate, you just take the commutator AB minus BA. That's actually the Leigh bracket of A and B in the Lie algebra works out to just this. And the proof is rather beautiful. So you take two curves that have respectively A and B as their initial velocities, both going through the identity at time 0. So bracket AB is supposedly going to be, well, I mean, this is not notation for the commutator at the moment. This is notation for that. So by definition, that's the derivative of this adjoint map, but that is the conjugate by this and that inverse, and then B. But of course, when I differentiate, I have the product rule. But this, remember, the inverse element goes with minus. That wasn't one of the first things we proved a while ago. So the derivative of the inverse is minus the velocity of the other direction. I mean, of the uninverted curve. So that picks up a minus, and then we get, of course, A of 0. Well, A inverse of 0, that's just the I. That's just I. But here we have big A and big A again, so we get AB minus BA commutator. So the Leigh bracket is the commutator bracket. So the commutativity of A and B reflects the commutativity of elements of G in the directions of A and B. So here's another proposition. Let A and B be in the Lie algebra. If the Leigh bracket, now we can say if the commutator of them is 0, then that also means that e to the TA commutes with e to the SB. And number 2, if e to the TA and e to the SB commute for all t and S in some little interval about 0, then it also follows that A and B commute, have a trivial Leigh bracket. So the proof is fun, as usual. So if that is 0, then, well, by properties of the matrix exponential, this is equal to that, but then you can add, so you can then undo it, and there you have it. Conversely, if I have that these commute for all t and s in some little interval, I can fix some time t, and I can look at the adjoint in the e to the TA direction, adjoint sub e to the TA of b. By definition, that of course is e to the TA, e to the minus TA, because that's the inverse of this, right? And let me scoot it up here a bit. So this is the adjoint. So here's like the G, so G, B, G inverse, all right? And, I say this is a neat trick. What's going on here? It's like people are always differentiating me. What do you mean? There's no derivative here. It's like, yes, there is. I'm the exponential of e to the SB, and you just couldn't see it. See, there it is. DDS, s equal to 0 of e to the SB. Of course, when you differentiate this, out pops a b, and then e to the 0 is I. So this is a very conniving way of writing this as a derivative and then pulling, so s and t have no dependence, so you can just pull the derivative out front. That is very snazzy. And then, of course, we can do what? Because s and t are where these guys commute, then I can commute these. And then these guys, well, it's the natural enemy. These annihilate in a flash of pure light, become the identity, and you're just left with e to the SB. That differentiates back to b, and so that then implies that the commutator is just 0. Do you see why? Well, why is that? Well, remember the definition. AB is the derivative of this, so if this is just constant, then of course the derivative is 0. All right. Very nice, very nice. So the commutator is a Leigh bracket, and so that's, as you study Lie theory more abstractly, you can approach it from a more axiomatic setting. Lie algebra is a vector space plus a Leigh bracket. Now that's a bilinear bracket which satisfies certain axioms, the Jacobi identity, usually on the list. Let's see here. So it's bilinear. So that's 1 and 2, and it's skew symmetric like this, and it satisfies this Jacobi identity. So the Jacobi identity basically measures a departure from associativity. All right. So two Lie algebras, G1 and G2, if you have a linear function from G1 to G2 of two Lie algebras, then that's said to be a Lie algebra homomorphism if it preserves the Leigh bracket in the natural way. F of Leigh bracket of A of B is the Leigh bracket of F of A and F of B. Here we're looking, of course, at the Leigh bracket in G1. Over here we have the Leigh bracket in G2. As you can see, a Lie algebra homomorphism preserves the bracket. In the case that F is a bijection, then F becomes a Lie algebra isomorphism. All right? And, all right, well, yeah, standard stuff. If G1 and G2 are matrix groups with the algebras G1 and G2, if F going from G1 to G2 is a smooth homomorphism, then the differential of F is a Lie algebra homomorphism. I found these theorems when I first saw them, I found them to be deeply satisfying. So you get this interplay between homomorphisms of the group and homomorphisms of the algebra, and sometimes you can go back and forth between these two worlds. The proof mainly hinges on two computational details. One, the chain rule as expressed for tangent vectors in terms of map compositions, and two, that the linear map dfi is its own best linear approximation. In total, if you're awake, it is a joy. Let us see that. Here it is. So here's the theorem again. Group homomorphisms gives you Lie algebra homomorphisms. So if I have A and B in G1, I can let A of t and B of t be a differentiable path, for which it goes through identity, and the velocity vectors of the paths reproduce A and B. Now, let alpha of t be the conjugate map by G of B of t, so G, B of t, G inverse for some G in G1. And note that alpha of 0, of course, is I. Furthermore, alpha prime of 0 amounts to the adjoint sub G of B prime of 0, because that's the definition of the adjoint is that adjoint sub G means that you take this and you package it by GG inverse, all right? Consider then the differential at the identity of F of the adjoint, and remember F is given to be a smooth group homomorphism here, okay, that's the assumption. So this differential, by definition of, differential, is the time derivative of this, composite. Because, well, how do I say this? I mean, that's just directly from what we wrote above, but well, again, this is alpha prime of 0, right? So df sub I of alpha prime of 0 is the derivative with respect to d of f composed with alpha. That's the differential in curve notation, all right? But this is precisely, let me scroll up a bit here. But of course, this is precisely that, because alpha of t was conjugation by g and g inverse. But then remember, f is a smooth group homomorphism, so that is f of g times f of b of t times f of g inverse, all right? And so then what? Well, the only time dependence you got is in the middle term, right? So this is, you can just kind of factor those out, and then you have, in the middle, you have the derivative of this piece, which gives you the differential of f sub I and b, and then you're looking at the adjoint of f of g, like that. All right? And so what? Well, that's equation 8.1 in TAP. Apply the result above, all right, to g equals to a of t. All right, so replace g with a of t. What do you get? You get that the differential, well, if you put g equals to a of t, this becomes commutator of a and b, all right, for one thing. And so what we get is that the differential of the commutator is dfi of this. Well, I mean, the commutator is defined to be that, right? But we also have that we can pull the derivative out here, and this is by the equation 8.1. Now we're using 8.1. We're going to go from here to here, right? And then this is exactly the, well, but what is this? Again, applying the definition of the adjoint. I mean, the definition of Leigh Brackett as it relates to the adjoint. This is the dfi, comma, dfi of a and b respective. But hey, that's exactly what we set out to prove that the differential is a Lie algebra homomorphism. See, it's taken the bracket here to the bracket over here. Now, dfi, of course, is at the tangent space the identity of G2, which is frac G2. In other words, this is the Leigh bracket in frac G2. This is the Leigh bracket in frac G1. And there you have it. So, let's see, I have a little bit of extra here. Noting, of course, that v of t equals, add a sub t as a path in G1, hence as dfi is linear, dfi equals d of dfi. So dfi of v prime of 0 is, which is ab, which is that, is equal to d of this, which is equal to d dt of that, which is that. So I think I'm adding something into one of these steps here, but I'm going to move it along here. Corollary 8.7. Oh, I think it's a good time to stop and start again.